Hello all. In the last class we were discussing about functional dependencies and when we have one relation, when we find out one functional dependency or a set of functional dependencies, how we can infer the remaining or all functional dependencies from the relation. Okay, so for that we define some rules IR1 through IR6 to determine all the functional dependencies. And now we move to the next topic from database design, disclosure and equivalence set. So today's outline is we'll be discussing and we'll be defining about closure of dependencies, and we'll again define closure of attributes also closure, and we'll give an algorithm for closure of attributes to find out closure of attributes, and we'll define cover and equivalence set. And closure. So what is meant by closure? So closure of a set F of functional dependencies is a set F plus of all functional dependencies that can be inferred from F. Okay, so we have a set of functional dependencies F, and we'll be able to apply this inference rules to infer set of all FDs from this set F, and we can call it as F closure. Okay, and what is the purpose of using this closure of functional dependencies? Okay, this will be used in database design using synthesis approach, that is top-down approach, and there database designs, the main focus is first we'll specify the set of functional dependencies that can easily determine the semantics of the attributes of it. Okay, and then we can apply. So we first define a set of functional dependencies that determine the semantics of the attributes of R. Then we can apply this inference rules. We have 6 inference rules, IR1 through IR6, that is used to infer addition functional dependencies that will also hold. So we need a systematic way to determine the additional set of functional dependencies. So for that, first determine each set of attributes X that appears as LHS of some functional dependency in F. Okay, so we take some functional dependency in F and we take left hand side of that functional dependency, and we are what we are doing is we are trying this each set of attributes X that appears as LHS of some functional dependencies. Then we will determine the set of all attributes that are dependent on this X. Okay, so we get LHS, and then we find out all the set of attributes that are dependent on this X. Which means also instead of finding the closure of FD, we take that dependency or any of the functional dependency from F. Then we take the set of attributes, we'll find the closure of that attribute set. Okay. So here that closure is known as attribute closure. Okay. Which means that is closure of attributes. That means closure of all attributes that are functionally determined by this X. So attribute closure means determine each set of attributes X that appears as a left hand side of some FD in F, capital F. Then determine the set of all attributes that are dependent on X. Okay, so we take each function dependency and then take LHS of that function dependency. Then we determine the set of all attributes that are dependent on this LHS. And that is known as attribute closure. Okay, and we can see some algorithm for that. So that is for each such set of attributes X, determine the set X closure of attributes that are functionally determined by X based on F. Okay, and this X closure or X plus, that is called the closure of X under F. Okay, so we take each such set of attributes X. So such set of attributes means the attributes in the LHS. Okay, then determine the set X plus of attributes that are functionally determined by X based on F. So we are trying to find out the set of all attributes that are functionally determined by this X, and we can call it as X plus. And this X plus is nothing but the closure of X under F. Okay, this is the detailed algorithm for that. So that is algorithm to calculate closure of X. And input to this algorithm is a set of F of uh, functional dependencies on a relation schema R and a set of attributes X, which is a subset of R. So we have a set of functional dependencies on a relation schema R, that is input to this algorithm, then a set of attributes X also, which is a subset of this R relation schema. So initially we can assign X closure equal to X itself. Okay, what does that mean? By using the inference rule 1, we can say that closure of a set includes that particular set. Okay, so X plus is equal to, that is assigned as X. Now repeat this until no more attributes can be added. So repeat all, we are defining alt X plus, that is equal to X plus. We are assigning alt X plus equal to X plus, and we will be changing this alt X plus here. And for each function dependency Y to Z in F, do if Y is a subset of this X plus. So we take each functional dependency, and we are talking about this Y, and Y is a subset of X plus. What is X plus? The closure already determined, okay, or partially determined. Then X plus is equal to X plus union Z. So we add the Z to X also. So we say that we have X, we start with X, and we call it as, initially we call it as closure of X, and we are trying to modify this X plus, and that is stored in alt X plus. So we keep this X plus in alt X plus, and we take each functional dependency in F, and functional dependency will be of the form Y to Z. Okay, and there suppose Y is a subset of this X plus. Y is a subset of this X plus, then we can add this right hand side to this closure also. So X plus is union Z, X plus equal to X plus union Z, and again what will happen, we'll add X plus to alt X plus. So finally we'll reach a condition where there are no attributes can be added. Okay, so alt X plus will contain closure of this X, and until X plus equal to alt X plus, which means we cannot add further. That is the halting condition. So consider one example also. Okay, so one relation schema R with attributes A, B, C, D, E, and that with some set of functional dependencies, then B to D, C to E, D to A. Now the algorithm is like this: X plus, we start with X plus equal to X, and we repeat until no more attributes can be added. Okay, so alt X plus equal to X plus, and for each function dependency Y to Z in F, do if this one Y is a subset of this X plus, then add z, that is right hand side of this y to closure. Okay, until x plus equal to alt x plus. So which means until no more attributes can be added. So consider here, take the first function dependency, that is AB. Okay, AB to C. So there we are trying to find out, we take LHS of each function dependency. Okay, so AB plus, so we get x plus. So here we take it as AB plus and x plus equal to, okay, and we add alt x plus as again this x plus. What is x plus? AB itself. Okay, so we take a x and consider it as closure of x, and that is copied to alt x plus. Now our alt x plus is AB. Okay, now take the function dependency AB to C. Okay, AB to C. So what will happen? We take, according to this condition, we can check whether the left hand side is a subset of x plus. What is the left hand side? Left hand side is AB. So AB is a subset of AB. Okay, because alt x plus is AB. X plus is also AB. So AB is a subset of AB. So now what we can do? X plus is equal to ABC. So which means we can add the C to AB. So we'll get ABC. X plus is equal to ABC. Now we take the next function dependency, that is B to D. So when we take B to D, again we make sure that B, that is the left hand side, is a subset of x plus. Okay, x plus is ABC and B is a subset of ABC. So what does it mean? The right hand side can be added to the closure. So D can be added to the closure. X plus is equal to ABCD. Okay, and take a third function dependency, that is C to E. So there we need to check whether C is a subset of x plus. X plus is ABCDE, that is a superset of C. Okay, so it means that E can be added to this set. So x plus equal to ABCDE. Now take the last one, D to A, and here D is a subset of ABCDE. Okay, D is a subset of ABCDE. So which means A can be added where A is already a member. So anyway, x plus will be, finally x plus will be ABCDE. Okay. So let's take another example for the relation schema R. Class, and class has attributes class ID, course number, instructor name, then creditors, text, publisher, classroom, capacity. Okay, so all these are the attributes of this class. So we have given 5 function dependencies also. Function dependency 1 is class ID, 2 course number, instructor name, creditors, text, publisher, then classroom, capacity. Okay, so class ID determines all this. All of the attributes will be determined by this class ID, and course number to creditors, then course number comma instructor name to text comma classroom, then text to publisher, then classroom to capacity. So let's find out the closure. The first dependency is class ID to course number, instructor name, etc. So we take the left hand side. So we are trying to find out class ID plus, that is closure, and we'll be finding out this based on the algorithm, previous algorithm, and we get class ID, then course number, instructor name, creditors, text, publisher, classroom, capacity. So which is nothing but the relation schema class itself. And we take uh, course number closure, that is course number comma creditors, then course number comma instructor name plus, that is course number, instructor name, creditors, text, publisher, classroom, capacity. There we do not have this course class ID. Okay, apart from that everything is here. So this class ID is nothing but the class itself. So we can use this class ID as a candidate key for this relation because that determines all other attributes. So now we move on to equivalence of sets of functional dependencies. So we are trying to define what is meant by equivalence of sets. Okay, so we have, suppose we have two functional dependencies, sets of functional dependencies. Okay, two sets of functional dependencies, for example, f and g. So we are trying to define what is meant by saying that f is equivalent to g. Okay. And for that we use the definition of cover. Okay, cover definition. So a set of functional dependencies f is said to cover another set of functional dependencies g if every fd in g is also in f plus. Okay. So it says that we have two functional dependencies f and we can say f and g, and we can say set of functional dependency f covers another set g. Okay, f covers g if every functional dependency in g is also in f plus, f closure. That is, if every dependency in G can be inferred from F plus. So it means that every functional dependency in G is also in F plus. So this G can be determined from F, or every dependency in G can be determined from F. So alternately we can say that G is covered by F. Okay. So G, every dependency in G can be inferred from F, or we can say G is covered by F. And this is a definition for equivalence. So two sets of functional dependencies G and F are equivalent if G plus equal to F plus, if their closures are equal. That is, equivalence means every functional dependency in G can be inferred from F and every FD in F can be inferred from G. Okay, so cover means that is defined for F and G, and we can say F covers G if uh, every functional dependency in G is also in F plus. Okay, and that is F covers G. And if we have F covers G and G covers F, then we can say F and G are equivalent. Okay, so equivalence means that every functional dependency in G can be inferred from F, and every functional dependency F can be inferred from G. Okay, and G, which means G is equivalent to F if both the conditions, that is G covers F and F covers G, hold. Okay, consider one example, that is F is equal to, that is set of functional dependencies F. We are given with two sets of functional dependencies. One is F and another one is G. F with functional dependencies A to C, AC to D, E to AD, E to H, and G equal to A to CD, E to H. And first goal is to check G covers F, or F is a subset of G plus. Okay, G covers F. So we can first check each FD in F. Okay. So that is F1 is A to C and plus in G. Okay, that is closure in G. So each functional dependency and find out its closure. So find out the closure. This is for F1 and find out the closure with respect to G. Okay, so that is find A plus in G. What is A plus in G? A gives CD. Okay, and we can add A also. So A plus in G is the set ACD. Okay, A gives ACD, A gives CD. So CD will be there and ACD will be. We cannot take E gives AH or E to AH because E is not part of the right hand side and that will not be included here. And we get ACD as closure of A in G, and this includes the right hand side C. Okay, so A gives C and A plus in G, that is ACD, which includes the right hand side C. And take the second function dependency F2, that is AC to D. AC to D. So what happens there? If we have AC to D, then again AC is taken and we are trying to find out its closure with respect to G. So AC in G means we have A to CD. Okay, so what we get, ACD will again be set, and that also contains the right hand side D. Okay, and we take the next function dependency, E gives AD or E gives H. We have two dependencies with E as the LHS. So get E plus in G. What is E plus in G? This E gives AD and E gives H. So E gives AH is there. So AH will be added. Okay, AH with this. So E gives AD, ADH, E, EADH, and A determines AC. Okay, so A is there, so A determines CD. So this CD can also be added. So the remaining set is E plus is EACDH, and which contains the right hand side AD and H. Okay. And next we can check. So first step was we cover G covers F. G covers F, it is, or F is a subset of G plus. So we check that. Now, so what is meant by covering a set? We say that every function dependency in G is also in F plus, or every function dependency in G can be inferred from F. And in that case G is covered by F. So here we can say that every function dependency is determined from this G. Okay, or inferred from G. And next step is second step is we check F covers G, or G is a subset of F plus. So check each FD in G. So G1 is A to CD, find A closure in F. It is with respect to F. So A plus in F is equal to, what is A plus in F? Okay, take A gives CD. So A has A gives CD, C, and we have AC. Now we get AC also. So AC gives D. So we get ACD, which includes CD. Okay, which includes the CD. So every function dependency is determined by this G. And G2 is E gives AH. E gives AH. So get E plus in F. E has E to AD and E to H. What happens? We get E to AD and E to H. That can be added. And we can say we have A is there, so A to C and AC to D can be added. Okay, when A to C is added, we have AC and D can be added. D is already there, so EACDH. Okay, and which contains AH. Okay, so which means GF covers G. So we can say F and G are equal. So we have started with two sets where the functional dependencies are different, but we can say that these two sets are equivalent because F covers G. Okay, all the functional dependency in G can be inferred from F, and all the functional dependency in F can be inferred from G. So we can say these two sets are equivalent. Okay, and that was the summary. That is, today we discussed about closure of X, cover, and equivalent set. Okay.